Now we move forward to our third session, exploring and analyzing quantum dynamics with generative AI. Yes, Miri Kenig from Tel Aviv University. Thank you.
Thank you. When discussing generative AI, the concept of scientific AI, the integration of AI in scientific studies, is one of the most intriguing fields, because in science, we often have not direct theoretical knowledge about the system, but we could have a lot of experimental data on how it behaves. So when looking at the capabilities of generative AI to create new data from examples only and automatically identify semantically meaningful features, it enables the exploration of the problem space in entirely new ways. That made us wonder, what if we take the same building blocks, but instead of faces, encode physics? Like here, for example. Here we see images representing quantum behavior, statistical particle positions according to a quantum process they went through. Imagine that we could play with meaningful features, only now on a graphical representation of the physical rules. Hypothetically, if we could control meaningful variables from observation alone, we would be able to study unsolved physical phenomena, quite different from traditional techniques. It may find patterns and relations yet to be discovered and accelerate the whole scientific process. So inspired by that, we studied the ability of such networks to learn correlative quantum dynamics. Correlative quantum dynamics take a central theme in modern quantum science and technology. It's called quantum walks, and it describes the evolution of quantum particles in some medium. Due to an interplay between quantum statistics, interparticle interactions, and disorder of the space, the propagating particles develop non-classical correlations or dependencies between their positions as they propagate across the medium. So an inherent challenge in this field stems from the complexity of the high-dimensional non-classical correlations required to describe, analyze, or simulate these dynamics. Is it possible to develop a model that will understand the quantum rules from observation alone, enable post-training exploration of the problem space, such that we could reveal underlying phenomena? And if so, how can we verify that real physics has been learned? Because one of the limitations of those models is that they seem to come up with convincing-looking things, but we don't know if it's true or not. That's a big problem for scientists and something that we had to solve. In the following, I'll show exactly how we dealt with it. But for now, if we get more concrete, the idea is to check if with enough examples of quantum behavior, the model would capture the physics and manage to get two things. First, the ability to restore valid examples, meaning generating new examples with the correct physics. I will tell you the ending. We tested it. The answer is yes. And second, enable exploration of the problem space by fine-tuning real physical parameters. And here as well, we found that the answer is also yes. Now, to understand the physical problem we addressed, I'll start by describing the classical problem. We're talking about a particle movement in some medium. What you see here is called the Galton's board. And the Galton's board is a device that demonstrates concepts from probability theory. We have balls falling through an obstacle course and collected at the bottom in a series of beams. Every time a ball hits one of the pegs, it randomly deflects left or right, as it has a 50% chance to jump left and 50% to jump right. Looking at the beams below, we will see the probability distribution of the possible positions for a ball that falls through this medium. In the classical case, we get the Gaussian probability distribution, so that the probability of the highest probability is to find the particle near the origin at the end of the evolution. Now, let's go to quantum. Here is the same conceptual experiment, only now with a quantum particle. So what is different? As a quantum particle can be in a superposition, its evolution is governed by the interference of all the possible paths it can take across the medium. As a result, if we want to know where the particle might be at the end of the evolution, we must sum over all of these possible paths. And that's why the probability distribution here looks so different. Now let's move to the case we gave the model to learn. Instead of one entry site, we have taken 10, it's called the lattice, added another particle, and let them evolve in time. The particles move from site to site along the progress as they jump between the pegs in the conceptual illustration. But when more than one particle is involved, the collective evolution is governed by the quantum interference of all the possible multi-particle processes. They feel each other, and as a result, they develop the non-classical dependencies between their positions. In addition, we add disorder to the space by setting different energies on each site. It's equivalent to changing the peg's positions to get non-uniform space. So you can imagine it as a chain of 10 potential walls with different depths, so that the probability of moving from one wall to another during the evolution is unequal and causes an even more non-trivial dynamic. One of the ways to characterize this dynamic is to look at the correlation map. The two-particle correlation map represents the dependence between the particles' positions, the probabilities of finding each particle considering the other at the end of the evolution. However, the correlation map is not enough when we want to teach a physical process. To verify if the learning is correct, we need to know what led to the final state that the correlation map represents and see if the model has learned the correct physical relationship between the two parts. So, for the training set, we prepared the images as follows. Think about it as a face, only now, unlike faces, each image contains two parts. One part defines the problem, and the second the solution. The definition of the problem is the vector on the left part of the image. It's a specific realization of disorder, 10 values of random energies for 10 sites that defines the particle's initial states and the progress medium. The right side of each image is the calculated correlation map, the result of the propagation after some time t, considering, of course, all the possible two-particle processes. Using simulated examples, we created a few data sets for different levels of interactions between the particles, non, medium, and strong, 0, 3, and 1,000, respectively. Start here with a specific initial condition in which the two particles are placed at two adjacent sites at the center of the lattice, and train the model. To evaluate the physics of the synthetic instances, we extract from each generated image the values of the lattice parameters, calculate the expected two-body correlation after propagation, and compare the resulting correlation matrix to the generated one. Our results indicate that the model can produce new pairs of random lattice parameters and the resulting correlations with the correct physics. So now we have a model that managed to learn the physical rules from observation alone and can invent a problem together with its physically right solution. We tested it for all the other data sets, and it also works. And now, as a proof of concepts for exploring the problem space, we use the truncation trick that you can see at the top right for faces. What we see here is that while the original network was trained on a disorder level of 3, corresponding to the rightmost histogram, using the truncation trick, we can produce new instances with different level of disorder. The algorithm identifies the relevant control parameter of the system that was not explicitly highlighted in the training set, and enables tuning its levels while keeping the physical validity of the generated instances. Once we've done that, a physical phenomenon was revealed. Here I show how I can control the levels of the disorder in the generated instances post-training and uncover a real physical phenomenon called Anderson localization, which is a crossover from almost free propagation at low disorder levels to localization in high disorder. Even though we didn't train on this explicitly, we get control of a real physical parameter of the system. Taking this technique a step forward, we trained the model also on the full two-particle problem. So far, what I've shown has dealt with the simplest yet non-trivial problem of two particles with a specific initial condition. Now we consider all possible initial states. The physical validity was now calculated using an exact physical formula of fidelity and done similarly to the previous process. We have achieved very good results here as well. This figure shows that in addition, a pre-trained network can accelerate the learning of new and even more complex problems. While the blue network learned the case of two particles with a medium interaction of 3, started from scratch, the red network starts from the blue one and uses its knowledge to learn the propagation of 3 particles with the strong interactions of 1,000. it's easy to see that it converges much more quickly. We found that here as well, the trained network identifies the disorder level direction in its latent space and reveals the Anderson localization phenomenon. And now let's recap. Over the past 3 years, we've seen dramatic progress in the field of generative models. They've seen an incredible burst of research, improvements, and applications. The developed algorithm I presented here managed to learn, imitate, and analyze complex quantum correlations. This enabled post-training exploration of the problem space, revealing underlying phenomenon, and accelerating the learning of more complex problems. These results demonstrate the great opportunity of integrating generative AI and physics and suggest a general framework for using generative models in physical analysis and discovery. I hope I was able to convince you that although many machine learning models are applied to scientific studies, generative AI holds the potential to change the way we explore, and it's definitely one of the most intriguing fields when looking at the vast spectrum of AI. Thank you.